All right, this is number 4. We're going to actually now really get into kind of the mucky muck of how neurons actually work. I'm hoping that at the end of these couple of presentations you'll have a much better understanding of how neurons actually work, how they function, and how they actually communicate with one another. We're going to actually start with the field that's called electrophysiology. So neurons work with electricity and they're helping your physiology. So the field is called electrophysiology. In your book, it looks like page 111 is going to be a map to what we do. We have some pictures and videos as well. The videos are relatively short because, I don't know, I always hated watching long videos. So, when we start with the neuron is the cell that basically sends electrical signals up to your brain. The first thing you need to note about this cell is that there's what's called a lipid bilayer. So if you look on page 111, you can kind of see there's kind of the outside and inside of a neuron. And they're little channels. Lipid stands for, fat double layer. And if you look on that little figure on 4.1, you can see there are little channels where little ions, which are charged molecules, can kind of go in and out of the neuron. So we know some very important things about the neuron before anything occurs, before any electricity goes through. So we're going to describe what's called the resting state. So this is the resting state. This is before action potentials happen, before anything happens in the neuron. The neuron is said to be in its resting state. And the book shares a lot of information, and it's all actually factually correct. But what I like to do is kind of give you the Reader's Digest condensed version. So the things we know about the neuron in the resting state. We have ions. Ions are charged molecules, and the things we know about ions is one thing that we know is that there's a lot more sodium, Na, that's outside the membrane. It's outside in the extracellular fluid, the membrane. The other thing we know is that there's a lot more potassium, K+, inside the neuron. So during the resting state, there's more sodium on the outside, there's more potassium on the inside. The other thing you need to know is that if you look at that figure 4.2, you can actually put a recording electrode inside versus outside the neuron. And if you do that, sorry about that, that was the phone. If you put a recording electrode inside versus outside the neuron and you measure the electricity, you would think that it would actually be a charge of about 0, but actually it is not. The charge inside compared to outside the neuron is negative 70 millivolts. Inside the neuron versus outside, it's negative 70 millivolts. And so that's another important thing to know. So 3 things so far. There's more sodium on the outside of the neuron. There's more potassium, K+, on the inside. And the inside of the neuron, the charge is negative 70, so it's actually at a negative charge compared to outside. The final thing that you should know is basically that if there's more sodium on the outside, what do you think sodium would want to do? Well, sodium would want to go inside the neuron. And there's more potassium on the inside, so what do you think potassium would normally want to do? It would want to go outside the neuron. But there is something that prevents that. There's a little diffusion where a little sodium does come in through those channel proteins and a little potassium goes out, but there's something called a sodium-potassium pump. And the sodium-potassium pump basically keeps the resting state. It makes sure it kind of puts sodium on the outside and potassium on the inside. So this is called the resting state. More sodium on the outside, more potassium on the inside, a charge of negative 70 inside when compared to outside, and the sodium-potassium pump is keeping that negative 70 balance. It's keeping the sodium outside and keeping the potassium inside. So that is the resting state, and if you look at the pictures that I attached and watch the little video, hopefully that will make more sense. The next thing, though, that you need to know is I said this is where the neuron is actually working to send an action potential. So I have to describe for you how an action potential is generated. So the first step is, remember the 3 parts of the axon? Okay, the 3 parts of the axon, the dendrites, the cell body, and the axon. Well, the first step is that these dendrites have to collect electricity. And they actually do that if you keep going ahead with the pages. Let's see what we got. It looks like around 114. And if you watch the video as well, the dendrites collect electricity. And the really important thing that you need to know is they all collect electricity. Do you remember where that summates? It summates in the cell body. And there's a key number in terms of how much electricity these neurons, these dendrites, have to collect. If these dendrites collect a total of 15 millivolts of positive energy, so if there are 3 dendrites and each one collects 5 millivolts of positive energy, that's called depolarization. If they all collect 5 and then they add up in the cell body to be 15, then the neuron will have an action potential. The cell body will send a signal out. So the basic principle that the action potential works on is called the threshold principle. The neuron must collect 15 millivolts of positive energy from the dendrites. If they do that, then at the cell body, if you reach this threshold, then an action potential will be generated. So it has to be 15 millivolts of depolarization, of positive energy. Do you know what that would put the neuron state at? Remember, the neuron started at negative 70 millivolts. So what is the threshold value that's going to lead to an action potential? It would be 55 millivolts. So as soon as that neuron collects 15 millivolts of depolarization, then you're going to reach 55 millivolts and then the action potential starts. So you need to collect 15 millivolts of depolarization. Once again, I'm hoping the video helps you out. Moving down in the outline, now we're going to go into, okay, when it starts, the action potential, what happens? So we're going to start with local structural events. So when the action potential happens, the whole membrane really changes in a major way. So if you remember that lipid bilayer, basically what happens, and the pictures in the book illustrate this as does the video, when it reaches 55 millivolts, that lipid bilayer really changes its properties. The first thing that happens is there are gates that open, these ion channels open for sodium. And so there's called selective permeability to sodium. Selective because it's just sodium, channels open just for sodium. And sodium, think about your life as sodium. You spent your whole life outside the neuron. What would you want to do if the gates open? You don't want to come in. There would be a sodium influx. So sodium is going to rush in to the neuron. There's going to be a sodium influx because the gates are being selectively permeable, got to use the terms, to sodium. And so sodium rushes in. And what do you think that's going to do to the charge inside the neuron? Well, if the neuron was at negative 55 for the start of the action potential, now that all this sodium is rushing in, what do you think will happen? The neuron actually goes from negative 55 to negative 25 to 0, and actually, since so much sodium is in, it becomes more positive. It actually goes into a positive realm. And once that happens, once the gates open to sodium and all this sodium rushes in, something else interesting happens structurally. The gates close to sodium, but then they open to potassium. Now, if you're potassium and you spent your whole life inside, where would you want to go? You'd want to rush outside, and that's exactly what potassium does. There's a potassium efflux. What? EFFLUX? There's a potassium efflux. Potassium rushes out, and then the cell kind of gets negative again. So the local structural event, sodium rushes in, and then potassium rushes out. It makes the neuron more negative again. And then as the last step in here, the sodium-potassium pump comes into play and kind of restores the balance. So you've got these local structural events that are going on right at the point of the action potential. And you can see the book kind of illustrating this as well. You don't need all the details of this, but those are the local structural event. And once this action potential happens, then there is a refractory period where the action potential can't happen again for, I think it's a millisecond or so. So that's the local structural. The book has a lot more details. You don't really need to know it if you understand my story. Next on the hit parade, what do we got? Signal transmission. And I think the book, once again, has a picture of this. So these changes are going on right at the local membrane level. But remember, And this is right at the start of the axon where the action potential is occurring. But remember what we said, when an action potential is generated, that signal has to be transmitted down the axon. And that's exactly what happens with the transmission of the signal. The name of the communication, and if you look on page 119, the name of the communication is called saltatory conduction. Basically, if you have an axon, it is wrapped with what we call myelin sheath. And the myelin sheath is basically fat, and it basically insulates the neuron, the axon, to allow quick cell transmission. So the action potential basically gets created from point to point to point. These points are called the nodes of Ranvier. And so at each point along the axon, the action potential is recreated. It's insulated between those points by the myelin sheath and transfers all the way down the axon. Now, if you're wondering about myelin sheath, if your myelin sheath isn't working right, which is what happens in multiple sclerosis, then the signals don't work correctly. So the signals go all the way down, point to point to point, saltatory conduction, to the end of the axon. And once again, the video should hopefully illustrate this, and the pictures as well. And now we're left with the signal being at the end of the axon. So in summary here, and I've been babbling along too long here, this is what we call electrophysiological information. We've been really focused in on how the electricity transfers down the axon. We know the neuron in its resting state has what? More sodium outside, more potassium inside, a negative 70 millivolt charge, and the sodium-potassium pump keeps that resting state. It puts the sodium outside and the potassium inside. If you collect 15 millivolts of depolarization collected by the dendrites, that'll be a threshold value. The neuron will be at negative 55, and if you reach that, negative 55, that'll start an action potential. If you only get 14 millivolts, it won't happen. If you have 14 millivolts of depolarization, 56 doesn't cut it. It has to be at 55 millivolts, and then you'll initiate an action potential. What happens locally? Well, we have a sodium influx because there's selective permeability to sodium. The inside of the neuron turns positive. We have potassium efflux after that. The potassium rushes out. And then we have the sodium-potassium pump restoring the balance and a refractory millisecond before this can happen again. How does this get sent down the axon? Point to point to point by saltatory conduction. It's insulated by the myelin sheath so that the signal goes really, really quickly, and it's recreated at each node of Ranvier. Hopefully you can type up that story and share with me the fact that you understand it using all the terms we have in neuroscience. And that will conclude the 12-minute recording. Thank you.